Hello, today we're going to talk about exponential functions. Now, unlike polynomial functions, whose terms have variable bases and constant exponents, exponential functions have constant bases with variable exponents. So, for example, what this means is that my function now would be f of x equals 2 to the x. My base is a number and my exponent is a variable. Or I might also have something like g to the x equals 2 to the opposite of x. So these would be two examples of some very basic exponential functions that we're going to explore in this unit. Now, one of the things you'll need to be able to do in order to work with exponential functions is to be able to evaluate these functions for exponents that are rational, irrational, all kinds of exponents. So let's take a look at some examples to kind of review how we would need to evaluate some exponents. Now, you remember what 2 to the 4th means. Again, what that means is that you have 2 times 2 times 2 times 2, or 16. Again, that's what an exponent means. But some may not be as easy as others to determine what they mean. 2 to the 1/2, that's one that should be somewhat familiar from our last unit of study. Another way to think of 2 to the 1/2 would be the square root of 2. Or we could also look at, say, 2 to the 3/2, which would be the square root of 2 cubed. Again, lots of different square roots that we could come up with when we're dealing with exponents. But what about if we had something like 2 to the square root of 5? That's very difficult to rewrite in another form. So for right now, we need to just be able to evaluate what does this actually equal. Well, 2 to the square root of 5 is approximately 4.71. And at this point in time, that's all we need to know about that particular calculation. So let's take a closer look at exponential functions. Let's start out with the definition of what an exponential function is. A function of the form f of x equals some base b raised to the variable exponent x is called an exponential function. Now, there's a few things that have to be true in order for it to be an exponential function. First of all, your b must be greater than 0. So your base will never be negative. The other thing that must be true is that b cannot equal 1. And so if you think about it, if your base was 1 raised to any exponent is what? Well, that's always going to be 1. And so when b is 1, you actually end up having a constant function, and it won't fit the pattern of the rest of the exponential functions. The other thing is that x is real. So our values that we plug in for x, just like every other function we've looked at this point, is going to be a real number. So let's start by looking at some examples of graphs of exponential functions. And I'd like to start by looking at f of x equaling 2 to the x. And I want to first find some values that I can plot. So if I make a little table of values here, where I have my x and my f of x, I'm going to need to be able to evaluate some numbers here. So let's start with my favorite number for x. What is 2 to the 0? Now you might have to think back a little bit to your exponent rules, but 2 to the 0 is always 1. let's say I plug in a 1 for x. Well, 2 to the 1 is 2, and I could do a few more. Let's try 2. Well, that's going to give me a 4. If I plug in some negatives, how about 2 to the negative 1? What is 2 to the negative 1? Well, we need to remember that negative makes it a fraction, so that's going to be 1/2. And 2 to the negative 2 is going to be 1/4. So we have a nice table of values here that we could go ahead and plot on a graph. So let's see here. We need to have some numbers on our graph. All right, so 0, 1 would be right here. 1, 2, right about here. 2, 4 is here. Negative 1, 1/2. Oh, that's approximately there. Negative 2, 1/4. That's even harder to show, right about there. Well, that's kind of interesting. Do you have a sense of what this shape is going to be? Well, it looks like we're kind of coming through like this, but what I'm really curious in is what happens beyond this point in this region down here. Will this graph ever equal 0 or be below the x-axis? Can I ever get a negative value coming out of the function 2 to the x? Well, if you look at the numbers we plugged in here, if I went negative 1, negative 2, if I went negative 10, 2 to the negative 10th is still going to be 1 over something. So the numbers will get very, very small, but the graph will actually never touch or cross the x-axis because this function will actually never equal 0. So it comes right along the x-axis here, and on this other side it actually increases very, very rapidly. So again, nice way to look at the graph is just to be able to plot some points. Now you might want to compare this a little bit with another function. Let's say that I wanted to take a look at g of x is equal to 4 to the x. Now again, if I were to look at some x and f of x values here, and let's say we look at the same x values we did here, you're going to get some similar g of x. Sorry, we're looking at g of x here, not f of x. If I plug in 0 for x, what's 4 to the 0? Well, that's actually still 1, so that matches what we had for f of x. If I plug in 1, I get 4. If I plug in 2, 4 squared is 16. If I plug in negative 1, I get 1/4. If I plug in a negative 2, wow, that's 1 to the 16th. So you'll notice that when we go to plot these, 0, 1 is the same place the last graph was at. 1/4 is actually going to go up a little bit more quickly here. 216 is like way up off of my graph here somewhere. So this graph is coming down much steeper than the 2 to the x graph did. Now if we look at the negative 1 and 1/4, you'll find that it also is going to approach your x-axis more rapidly than the first graph did as well. So as your base increases, you'll notice that the numbers get larger much more quickly or quite a bit smaller much more quickly. And again, that's all because the base is changing here. Okay, let's take a look at a couple of other graphs. Suppose that I wanted to look at f of x equals 2 to the opposite of x. Now if you think about what you've learned in the past with a negative sign in a function, what effect is this going to have on the graph? I'll let you kind of think about that, and we'll come back and answer that in a moment. But let's go ahead and make a table for this one as well. So again, I'm going to use the same values I did before. They're kind of my favorite values. But now when I plug in 2 to the opposite of 0, well, that's just 2 to the 0 still, which is 1. If I plug in 1, 2 to the negative 1 is, that's interesting, that's 1/2. 2 to the negative 2 is 1/4. 2 to the opposite of negative 1 is actually 2 to the 1, which is 2. And 2 to the opposite of negative 2 would give me 2 squared, which is 4. So notice the relationship you can see here between these two table of values. You'll notice some things have interchanged. So let's compare the graphs here. So let's see, 0, 1 is right here. 1, 1/2 is right here. 2, 1/4, closer yet. Negative 1, 2 is up there. Negative 2, 4 is even further up. So it looks like the graph is doing something like this. So compare these two graphs for a moment. Notice that this one ends up being a reflection across the y-axis. So we talked about this in Chapter 3, that negative sign, when it's by the x value, is a reflection across the y-axis. And that's exactly what's happening with this exponential function. It ends up being a reflection. Now there's one other thing to be aware of with this particular exponential function. There's a couple ways that this can be written. So a special note to make here. 2 to the opposite of x can be written as 2 to the negative 1 raised to the x. So it could also be written as 1/2 raised to the x power. These two both represent a reflection around the y-axis. So this, if you recall, is based on our exponent rules. So if you don't remember, there's two exponent rules that I've used here. The first is that if I have a to the negative 1, that is equal to 1 over a. And the second rule I've used here is the multiplication or power rule, where if I have a base raised to an exponent raised to another exponent, it's that base raised to the multiplication of those exponents. So we want to take a look at that very, very carefully when we go to summarize what happens with graphs of exponential functions. So let's take a look at that next. Okay, let's see if I can get this to